So last session was left with the problem at the end. The problem goes like this. So you had a blood test which was 95% effective, which was 95% effective. So by that I meant if there is a certain disease, if a patient has that, so 95% of the times the test will detect that the person is diseased. Okay, so out of 100 people, if they have the disease, 95 people will get their tests accurate that they have the disease. Maybe 5 people will miss out. So the test also yields some false positives. So what's the meaning of false positive? That means if a person does not have a disease, the test will still say that it has disease. So the false positive rate is 1%. Okay, 1% false positive rate. And the total population that actually has this disease is 0.5%. So 0.5% of the population actually has the disease. So now what we have to compute is, we have to, if a patient goes and gets his test done, and the patient's test comes out to be positive. So patient's test comes out to be positive test. So we have to compute the probability the patient actually has the disease. Patient actually has the disease. This is the question for you. I'll give you 2-3 minutes to ponder over it, and then at least tell me the approach. How will you approach the problem? So now let's do this problem. So if you see, first we'll introduce some notations. Okay, the notations will be, so let's suppose D will be the event while the person will be tested it has a disease. So I would have said positive, but it will collapse with P. So D basically means patient has a disease. Patient has the disease. Okay, and let's call the event E as an event while the patient was seen as positive. Okay, this is the first thing is I introduce some notations. Why are notations important? Again, I'm reiterating this point. Our brains are easy to sort of perform algebra and do these mathematical operations when we see symbols and numbers, rather than having some verbosity, having a sentence. So now, what is that I have to find? I have to find probability of disease given the evidence. Probability of disease given that the test was positive. This is what I have to find. And in terms of Bayes theorem, this is called as posterior. Okay, so I have to find posterior. Now, how does Bayes theorem relate to this? So Bayes theorem says that I can find it like this: probability of, if I even let's suppose use without even Bayes theorem, if I directly use conditional probability of D E. So this is intersection divided by probability of E. So now you know this, you expand by Bayes theorem then. This is equal to probability of E given D multiplied by probability of D. Okay, so this is probability of evidence given the disease. Okay, and multiply probability of the disease divided by, this is the probability of E. So this probability of E can be written like this. So let's suppose this is evidence. So this, there are two cases now. So people will have disease or they will not have disease. Okay, something of this sort. So they have disease and they do not have disease, and we can get some evidence. So I said, if you see some problem like this, so break the problem into smaller sub cases. So here I have two sub cases, D and this. So I'll separately write this P of E. Let's go to P of E and come back over here. So P of E will be equal to then. So what will it be equal to? Probability of intersection of this part. So basically this and this. So I'll perform the probability of D intersection E plus probability of D complement intersection of E. Okay, so this is disjoint, so I can use the additivity principle to directly sum the probability. So that's what I have done. So I break down this evidence into two things: have disease and do not have the disease. Now this thing again can be used. So we have also seen under theorem, the multiplicative rule. So where we said that, so this thing can be written as probability of evidence given disease multiplied by probability of disease plus, so this thing can be written as probability of evidence given there is no disease multiplied by probability of not disease. So this is the denominator that we can put to her. Now our equation becomes probability. We have to find probability of disease given the evidence, probability that patient is diseased given we got the evidence, we got the test as positive. So this is equal to, given the disease, so this is equal to probability of E given D multiply probability of D divided by this term over here, this term, this whole term. So this whole term basically is probability of E given D multiplied by probability of D, that is this thing is appearing again, plus probability of E given D complement, probability of D complement. So now you have to just plug in values. So how to plug in these values? Pretty easy. So probability of evidence given disease. So how much is that? 0.95. Probability given evidence, probability given the disease, probability of evidence given the disease. So that is how much is the test effective rate. Yeah, how much effective is the test? If there is a disease, so how much many times will the disease be detected? That is 0.5. Okay. So what is the probability of disease? So that is 0.05%. This is multiplied by 0.005% divided by, again the same thing over here, probability of 0.95 multiplied by 0.005 plus probability that patient is not diseased but still the test shows positive, that is this was false positive. So here you can use the false positive. So false positive is 0.01, and then how many population does not have the disease? That's 95% population doesn't have disease. 0.995. I think 0.05% have the disease. You have to just 100 minus that much. I think this comes out to be this much. So the answer over here is 0.323%. Okay, or 0.023, and this is around 32%. So this is pretty low if you see now, and even I have given the numbers as high. Okay, I hope you were able to understand this. Any doubts on this? So what I say is when you are facing with these problems of probability, so it makes sometimes sense to bring in numbers. Use, as I said, use some easy and extreme examples to fit in. So here what we can do is we can take an example, but you will have to help me in the calculation. Somebody have a calculator with you. Okay, maybe bring up Google and perform the calculations, otherwise I'll make the calculations wrong. So we'll do this by an example. Let's consider we have 1,000 people. Okay, so we have in total we have 1,000 people now. So we are not thinking through the Bayes theorem, we are thinking now through the numbers, and we'll see can we derive the same result. So we have 1,000 people. So tell me how many percent of people have this disease. So now the percent of people that have the disease is this much. So we have 0.5% population. So can you tell me the number? Anyone who has calculator? Fahad maybe? 0.5% among 1,000, these many people have this disease.
5.
5 people have the disease. Okay, have the disease. Okay, now we'll go here. So we are saying that if 5 people have disease, let's suppose these people will get tested now. These people will get tested. So out of these 5 people, let's suppose all of the people are getting tested. Let's say all of the people are getting tested. So out of these 5 people, how many people will actually get the test as how many people will be the test as positive? And now we have two types of people. The first person is actually disease and not disease. So these are 5 and these are 9995. Okay, so can you now tell me when the test is performed? So when the test is performed, so 95% of the people will be detected as disease. So how many people among these people will be detected that they have the disease? So 95% of this. So how many people then? Test
4.75.
4.75. Numbers are not coming pretty well, so it's all right. So among these people, when they get tested, so how many percent of people will still be asked that they have disease? So that is this number, the sensitivity rate that we have false positive, 1% of the people. So what is 1% of this? 9995. Calculate this. It'll be around 95, is it?
9.
Nine?
So 9995, no?
999, yes, 9995.
99.95.
99.95, that's what I said. This you have to put your over here. So this is for how much people the test said that they are positive. Okay, but actually only these people are positive. Only these people are positive. Okay, these things are false positives. Okay, now given the positive, what is the evidence? You'll add these things. So add 4.75 and add these 4.75 plus 99.95 and you calculate this. So this is basically probability that person actually has a disease given the evidence, given that the test was positive. Can you calculate this number? The calculation mistake that we did was over here. So it was written 9995. So it is actually 995. So now the false positive rate is 9.95. Now if you see probability of disease given that test was positive is 4.75 divided by 4.75 plus 9.95. This exactly comes out to be the number that we got from the Bayes theorem. So how do I told you how to remember the Bayes theorem is like this. So you have a square of this sort. Okay, then you have some hypothesis. This is your hypothesis. This is probability of hypothesis. Okay, you have some hypothesis. Okay, this is the whole population. And then you have probability of probability of evidence given hypothesis. Okay, that's the likelihood. The likelihood, let's suppose it fits this much. So this over here will be probability of evidence given the hypothesis. We assume the hypothesis to be true, and then we say, okay, what is the evidence? How much of the percentage of the evidence fits this hypothesis? So that is this much. Okay. Then over here, let's suppose this is the other part. So where the evidence like maybe fits and hypothesis doesn't hold. So we're saying this portion. Let's suppose this much of the portion is the probability. This is, let's suppose, not for the hypothesis. So what you can write is not simple is something like this, not the evidence or not your hypothesis. So if you somehow remember it like this, so you have to compute the posterior probability of a hypothesis given the evidence. Okay, now you know that only this much fits the description, only this much. So this red portion, okay, divided by these two portions. Okay, so these two portions is, one is this red portion, so I'll make it red. Okay, and this is red, and the other part plus this purple portion. Okay, so this part over here. So how do we come to this? So this probability basically is probability of E given H multiplied by probability of H divided by, again, the same thing. This basically is probability of evidence at the bottom, because you have two cases where you have this hypothesis, where you don't have this hypothesis, where the hypothesis holds, where the hypothesis does not hold. So you have these two cases, as we had these the patient was diseased, patient was not diseased. So that's what I wrote over here. Okay, two cases over here. So this is how you can derive again the Bayes principle from the you can derive the Bayes theorem for the first principles even by just looking at this diagram. So okay, and this is somewhat similar that we did in the previous session as well, where I took the example of farmer, and then I said we have two ratio of 200:10. So these many people, the 4 people are fitting the description over here, the 10 people are fitting the description over here. Okay, so I think 20 people were fitting the description. So total was 4 divided by 4 plus 20. Okay, so basically this portion was this. The probability of evidence given the hypothesis. So you assume the hypothesis to be true, and then you are saying hypothesis is given, what is the probability of evidence now? That's why I said likelihood. This is called as likelihood. Okay, then I said, okay, then you have to multiply with the probability of hypothesis. Okay, this is probability of hypothesis. Then you have to compute the probability of total evidence. But you know, this is from the total probability of evidence. So what you can compute is, you can say the evidence spans through multiple of this, might happen and even sometimes here we may have more than 2 terms, we may have 4, 5, 6 terms. So it comes in the summation part as well. So this is probability of hypothesis given the evidence. So this is called as posterior, and this is our prior belief. This is called as prior, and this is our total probability. So all these terms have their names, and now you understand also then. There are, as I said, there are different ways to understand Bayes theorem. The initial intuitive ways directly come up with the numbers. Then you can see how do we update belief. So we had this prior, okay, the prior of this, and then we said this is the likelihood. Then we changed it to some posterior. Okay, this is the posterior, and then we said, okay, this is how to compute total probability. So in total probability, what you should remember is that in total probability, you basically break down this probability, and you try to come up with the sub problems which are easier to solve. Okay, and that we showed over here also, that we showed in this case. So we had to compute probability of E, then we broke it down into 2 steps. So again, relating with this example, we had 1000 people, 0.5 there, and we just did it with some people. So if you again do this example, you once you watch the lecture again, you keep on doing this calculation, but parallelly try to fit in with this calculation, try to see this calculation as well, try to see, okay, these are 1000 people, that means what is the given, this is total population. So this you again do it with the symbols, because this is easy to understand by the number. That's how our brain is wired. But in order to generalize it, so then you would generalize it parallelly, and you will land at this formula. Okay, I hope you understood it. This is pretty easy, and you know there was a survey done in I think in Harvard. So they asked a lot of doctors the same question. They asked maybe some with different numbers. So nobody actually guessed the correct number. They were saying around their answer was around 90-95% should be the rate, something of this range. Okay, and this is the state of doctors, because the doctors, if they are not trained in probability, so they'll come to these conclusions. But what if, like, this result sometimes seems counterintuitive and sometimes encouraging also. But let's suppose if some people have now symptoms also, if they have the symptom and they are getting tested and it comes out to be positive, now the symptom should be considered as an evidence again. Okay, now you should not have the prior this, you should not have prior knowledge that we had, I think 0.05 this. You should not have 0.5% of the population has the disease. Now you got symptoms. Basically, symptoms are again the evidence. If doctors are using it, so if any of you maybe have a doctor, maybe cousin or something, so if they are using it, so how should they use? If a patient has a symptom, so prior probability should be again changed. Okay, prior should be updated first based on the evidence, because you got this symptoms, so now it increased your probability, it increased the prior. Okay, and you have to again use the Bayes theorem to update that, and then you can say if your test comes out to be positive. If your test comes out to be positive, then probably you have the disease, because now you also change the prior. And one more caveat here is that let's say if you got the test done and it comes out to be positive and you had no symptoms basically, so after that what you can do is you compute the probability, it came out to be 0.3. If you again do the test, if it comes out to be again positive, so you will see that this probability will shoot up. This probability will say that now there is a lot of things that like there is huge probability that you will have a disease. I think it touched down to 90 or something. You can do it on your own. Now you can take your prior to be, let's suppose 95, and then you can see how much probability will shoot up. But the question there is, in the first place, if the test got you wrong, it might have the same reasons in the second time it would have got you wrong. So it is better when you are doing these sort of things, you should not do the same test twice. You should do one type of test once, and if it gives the probability of something, then in order to see the next evidence, the evidence should not be on the same test. You should get the separate test done. You should maybe the test should use some other technology, or test should use some other mechanism of detecting whether there is a disease or not. Otherwise, you will fall into the fallacy that maybe whatever happened wrong in the first test, same thing is getting repeated in the second test as well. So it is not a guarantee that if the probability is saying that probability is 90%, now you have the disease. So it is better if you have to perform test multiple times, do it with the different types of tests. I hope you got the intuition behind that also. So here what I can do is I can now code the same thing, because it's pretty easy. Let's suppose if some people are confused, the probability seems counterintuitive. So what can you do? You can write a little simulation, and the simulation will tell you directly that whether you are right in terms of probability. But you'll have to consider the prior into the account. Okay, and all of these things that I mentioned should be taken into account. So the first thing that we'll do is we'll import NumPy, and we'll import our random. So these are our modules that will be used. After that, what I can do is I can set these parameters. Whatever was given to me, I'll say number of patients we had. Let's consider this as 1000. Okay, we are simulating it for 1000 patients. Then I'll say disease prevalence. So we'll say, let's suppose a 0.5% population has a disease. So I'll say disease prevalence is equal to 0.05%. These many people have the disease. And then I'll say test sensitivity. So how much good is the test? If a patient is disease, so what is the probability that he actually will, basically true positive rate. That's what the comment showed. And false positive rate, that's also mentioned over here, that is 0.0. These are parameters I have been given. Okay, let's write a function, run simulation. So run simulation basically will tell you, and we'll simulate the whole process. The first thing is we'll keep on a counter with true positive and false positive. So true positives means where they actually had a disease and the test also said that they have a disease. That's called true positive. And what is the false positive? False positive is if the patient does not have a disease, but still it was detected that they have a disease. That's called false positive. Okay, now what can we do is we can write a loop for all the patients. So we'll write a loop for all the patients. So that's what I'm doing is we'll run a loop for all the patients. That is for 1000. We'll run this loop. I'm just copy pasting code to ensure that I don't make any errors while typing. And then I'll say has disease. So how many people has disease? So I'll just from random I'll say this. So this is has disease equal random.random less than disease prevalence. So these many people should have disease. So this is what I'm taking. And now what I'm doing, I'll perform the test. Okay, if the patient has disease, I'll perform the test on the patient. So this will ensure that only these many people have the disease. This will ensure from the number of patients. So I'm saying if patient has a disease, test result positive, if test result disease. So based on the sensitivity here, I'm saying that test positive is equal random again. Okay, but it is now based on test sensitivity. Okay, test sensitivity. So it will if patient has a disease, for 95% of the patients it will detect the disease. Okay, and that's why I'm saying if the test was positive, then +1. So you are detecting this plus positive. And then I'll one more thing that we have to do is for the other patients who are not let's suppose that for them if there was the test was they were not having the disease. So what I can do is else. So else if the patient does not have the disease, so what and test reveal positive for them. So how many patients will reveal positive? Basically based on this number. Okay, and now I'll increment the false positives. Okay, these false positives. Now what I have to do is I just have to calculate total positives is total positives plus false positive. These will be total positives. Total basically people which were detected to have the disease. That is what we did on the calculation with 1,000 people. Okay, total positives. And now if I have to calculate probability, the probability will be calculated like this. Pretty easy. You have to now only divide. This should be out of the loop. So if total probability is greater than 0, the probability of this true positives divided by this, and then you can return these things. Let's return. Okay, and let me return of this, and then I'll run the simulation. So here I'll paste the code for running the simulation. So here you can see this. And I think I have also performed the calculation from theoretical Bayes theorem. So this is theoretically what Bayes theorem is saying. I'm again using the same formula, and this is the simulation. This is the simulation part. I'm giving 100 this, and I'm storing all the results and giving the probability. Let's run this. And we have seen the patient number of patients is 1,000. All of this. If you see this, this comes out to be probability from a single simulation, and average probability across 1,000 simulations. In the single simulation, it can be wrong, and when you do across 1,000 simulation, so 1,000 patients basically, so that probability comes out to be 0.32198. And when you see theoretical probability, this is equal to this. Okay, the more number of patients you increase, that means the better this number will get. So this is pretty easy probability wise. So if you have to perform simulations, you directly bring up the code and maybe write the simulation, perform these trials continuously, and whatever the experiment says, do it as if you are doing in the real world, and you will come to know that Bayes theorem actually is correct. Okay, I hope with this simulation you got a better understanding of the thing. You at least now are intuitively correct. And so I asked you people, because now you have foundational knowledge of probability. I asked you people, what is the ballpark figure? Almost everybody of you got accurate now. So as I said that, other questions you'll have to do on your own. Now we'll see what are the mistakes that people usually do in probability. Okay, you have to be cautious. So I'll write word of caution. Oops. Word of caution. What people basically do, because probability theory, it plays a very important role in decision making, and sometimes a lot of mistakes are made because of wrong assumptions, sometimes because of wrong notions, wrong understanding of probability. So you should be very aware of these things. So because when you are solving problem, or when you are taking a decision in real world, so you should be knowing if I am making any assumption that's wrong, or if I am making any like fallacy. So one of the things that I have briefly discussed is called as prosecutor's fallacy. So prosecutor's fallacy. So it is very wrong to put just on prosecutor, because all the people make this mistake. So what is the mistake basically? People mistake this. So we have probability of hypothesis given evidence. So people mistake it with probability of evidence given hypothesis. Okay, so this is very common. So very common in courtrooms where people, well, let's suppose people have to prove, given the evidence, so they found some evidence and they have to prove whether a person was innocent or not. Probability of being innocent given the evidence. Okay, they confuse it with probability of evidence given the innocence. Even if I tell you, like, it doesn't seem if I tell you verbally this, so it doesn't seem a fallacy, but when you dig deeper, it is a fallacy. So one a very famous case was Sally Clerk's case. Okay, so it was a tragic misuse of probability. Okay, I'll say tragic misuse of probability. So what basically happened in that? So Sally Clerk, she gave birth to two sons, maybe once in 1 year, and in the next year she again gave birth to one more son. And then they had what is called as SIDS. This is called as sudden infant death syndrome. Okay, sudden infant death syndrome. Okay, it's a very natural cause and a very rare natural cause for infant death. So the prosecution argued that the probability of two of these deaths happening simultaneously is 1/73 million. This is what he argued. Okay, and this he used it as an evidence of the murder. So Sally Clark was then convicted because she had done murder and she was jailed for this. So what the rationale behind that was, she said, okay, this is 1 divided by 80, in 1 divided by 83,000 people or 85,000 people, this happens. 8,500 people. So so SIDS happens in 1 divided by 85. So I don't know why he come up with this number. So okay, let's assume for the sake of simplicity, it is the number. So 1 in 8,500 people get this sudden SIDS, sudden infant death syndrome. So if it is now 2, so he said, okay, now we should multiply it like this. He said, so first infant was died, so this much probability. Second, this much, and then he multiplied. So he basically assumed independence here. So he said these events are independent, assumed independence. Again, a fallacy. Okay, how are they independent? If the first child died because of some issue, maybe the same issue was with the second child as well. So here this independence should have not been assumed. But anyway, let's assume it. So he said now the probability is this 1/73 million. Okay, so what basically he computed? He computed probability of evidence given innocence. Okay, this should have not been computed. The probability of innocence given evidence should have been computed. Okay, so what should have been computed? Probability of evidence given innocence was computed. The computed thing should have been probability of innocence given evidence. And you know how these two things are related. They are related by Bayes theorem. So they should have actually computed probability of event, this innocence, multiplied by probability of innocence divided by probability of evidence. That's what they should have computed. And now in here, you know, this is pretty high. Probability of innocence. Why? Because how many mothers do kill their children? So the prior belief was very high. So this probability, even if he made this wrong calculation, still the probability would have come to be very low. Why? Because of this prior belief. The prior belief was very high because very less mothers kill their child. Okay, and because of this, she was jailed. And somebody, I think after 2 years, came to know about this and they made the right calculation. And after that, she was released from the jail. But it took a lot of mental toll, and it was a traumatic experience for her. And after that, she committed suicide. So in the court of law, people sometimes, because the judges don't understand probability, the prosecutor and let's suppose the lawyers also don't understand probability. So there are separate books written on probability for lawyers, probability for judicial systems, things like that. So if you're interested in that, you can go through those books. But you can strongly maybe benefit, you can take an unfair advantage if some people know about this, so they can use this in the courtroom. And if the judge doesn't know this, probably he'll believe. And sometimes we all the time do it. So in our day-to-day life, we do a probability of, what we do is we almost do all the time this probability of evidence given the innocence. Okay, we many a times do it because we confuse with these two things in real world. Okay, but somehow, because our brain is Bayesian, so let's suppose probability that let's say Mahmood is a good person, given I am getting some evidence. People always do it. So let's suppose you will assume something about me right now. So God forbid if I do some very bad stuff tomorrow. So what will happen is, the probability of me being good in your mind was having some value. The probability me being good given evidence, you should compute this. And then if I did some bad stuff, so you'll say, oh, he's not that good as I expected. Okay, you update the belief. So if I did much better good, so your probability should increase. So you'll say probability that sir is good given that I got more evidence. Okay, so I increase the probability, because our brain also think like this. The more examples, the more proofs that we get, the more belief we will have. So if we spend more time with people, that's why we get confident about their behavior. We're saying that he did this, and we collate all these things and we update our beliefs behind that. And initially we have a notion of let's suppose if you go outside, for certain states you have a belief. Okay, let's suppose for a state like Kashmir, you have a belief that Kashmiri people are hospitable. And then when you see some evidence, when you go there, if you actually feel hospitality, so you will increase the probability. You'll say, oh, I had this prior belief, I was thinking the probability there being hospital is only 0.5. Now if I saw that, now it shoots up. You'll say the 0.9, 0.8, something like this. Or maybe reverse can happen. If you had a bad experience, you'll say probability they're hospitable given that I saw something. Okay, because our brain is Bayesian. You can see that now. Given these examples, you can see we almost think in terms of probabilities. Okay, as I said, the probability is a measure of belief. Okay, this is one error that you should avoid. Caution. The first caution is, do not confuse this posterior with the prior. Okay, do not not posterior, posterior with the likelihood. Do not confuse those two things. Okay, so if you see people using it on day to life, you can just catch this logical fallacy now. And the second thing is, sometimes what people do is people also confuse posterior with prior. So this was posterior with likelihood. Some people say that if event A happened, they'll directly write P of A is equal to 1 now. This is pretty wrong. Okay, so this was our prior. So once A happened, you cannot write probability of A is 1. So you should basically write probability of A given A is 1. So this should be written. But this directly writing this is wrong, because in sometimes mathematical formulations, people will see formulation and they'll see probability of A. They'll assume, oh, A happened. Oh, that means probability of A is 1 now. Okay, but this is not correct. What actually is correct is this: probability of A given A is right. Probability of A given A is equal to 1 is right. So this is not, this is wrong. And while just plugging in the formula, plugging in the values in the formula, you should be very cautious about these things also. So probability of, if something event happened, you will directly write probability of that event is 1 now. No, probability of that event given that event happened is 1 now. You will have to be very careful with the notations as well. Okay, so I'll keep you giving these words of caution once we go to different topics of probability, because there are a lot of things that people either assume and make mistakes about these, and we should be well versed about these things, and some things which probably I have not encountered, and if you have encountered, do let me know that. We also get confused over here. Okay, do let me know about these are the errors that I have seen me committing. I am writing those, and other people who are writing books, and they also mention such and such these things. So if you come across some errors while making an error, then you figured out, okay, this was the error. Now you can also bring that down to notes, and we can also write that down. Any questions still here? Let's now go to one more problem that we'll do by using Bayes here on conditional probability. That was Monty Hall's problem. So initially, we're giving an intuitive explanation to these, and then we're convincing you based on the simulations we performed. So for this medical case, and we also did a simulation now, and then also showed you how to do it by using conditional probability. Similar thing we'll do with the Monty Hall problem. So now I'll directly go to the right solution. Right solution, how to think about these problems. Now you know that there are 3 doors in this. So there are 1, 2, and 3 doors, and one of these is price. Okay, and there are books written on Monty Hall. Okay, you can just search online books on Monty Hall. There are books written on Monty Hall probably, because it was so confusing for people. There were people who were having PhD in mathematics, and they were giving wrong answers to this. And some lady actually wrote a right answer, and she was scolded so much. She was saying she's stupid, she's giving wrong answers, and this and that sort. But the easy way could have been just perform a simulation. Do a simulation, and you will get to the right result. And we have done that, and we have got some intuition. Some people, once they listen to this problem, they think, oh, I have understood this, and then they get it wrong. Okay, they give an answer, it's completely counterintuitive, and after one level comes where you think, now I have understood this, and after thinking it again through, you are thinking, oh my god, I am all nuts again. So it is better to perform the simulation to convince yourself first and get the right intuition. There are many wrong intuitions going around also, so you can also think it wrongly. So it is better to know about the right intuitions. Now we know that there are three doors. One of the door has price, other two has no price. So host opens the one empty door. Once you choose the door, the question is, do you want to switch? So how can you use? I told you can use tree diagrams also. So when there is process is sequential, what you can do is you can use a tree diagram to solve it. Okay, we'll also use that, and we'll maybe also use total probability. We'll see. Let's suppose we'll assume that I'll choose one door, because the problem is symmetric. I can choose any door. I can choose 1, 2, or 3. Let's suppose the choice is, this is what I choose. I am choosing door 1. Now the car door, the door which has the car, it can be 1, 2, or 3 with equal probability. That is 1 by 3, 1 by 3, 1 by 3. Same thing will happen for 2 also. I could have chosen second door, I could have chosen third door, but it is one and the same thing. Okay, if I choose the one first door, so I'll write it choose over here. So I'll write the car door over here, the door which contains the car, and then I'll have to write Monty's door. So Monty Hall basically has to open a door. I'll also have to write his door. So now I chose one door, and the price is also in one door. The Monty has the two choices now. Monty can open 2 or 3 doors. He can open either door 2 or door 3 with equal probability. Assuming here that Monty just randomly selects it because he knows that now these 2 doors are empty, so I can choose with probability half, one half, one half. There are other versions of the problem where Monty Hall is a bit lazy, so the door which is closer to him, he opens that one with higher probability. Okay, you can also think of those versions of the problem and do it accordingly. The second thing, if I chose the door 1 and car was in the door 2, okay, so the Monty is now forced to choose door 3 only. He is now forced to choose door 3 with 1 probability. He has no other choice because I selected 1. The empty door was 3 and 2 had the price basically. So he is forced to just open door 3. Now for the 3 door, same case. The car is in 3 door. I have chosen 1. Now he's forced to open door 2 because this is the only door which is empty. He has to choose with probability 1. Okay, now what we have to compute? We have to compute probability if we switch. Probability of winning if switch. If we switch, probability of winning given that Monty opens the door. Monty opens empty door. This is what we have to basically compute. Probability that I'll win if I switch given that Monty Hall opens one of the empty doors. Okay, so what I can do is here, let's suppose I'll do it case wise. So I'll say, okay, I have chosen one door. Okay, I have chosen this door 1. Let's suppose door 1 has the price. Say door 1 has the price. I'll fix this. Okay, and basically now based on that we'll have to either we can see Monty can choose 2 or 3. Let's suppose Monty has to open door number. Let's suppose he opens door number 2. Okay, for this now Monty opens door 2. So he opens door 2. So this event now happened. He opened door 2. So we have to see probability win if I switch. Okay. So what is the probability of winning if I switch in here? So you have to basically what you have to do is you have to multiply these things. So if you see, I'll calculate the probability along all these paths first. The probability of this path. So I chose 1 and the car door was having price 1 and then Monty Hall chose this. So this path I have to choose. This is 1 by 3 multiplied by 1 by 2. So this is the probability. So basically I chose 1, car door had price 2 or Monty Hall opened 2 because these are the two things that I am assuming. I am assuming that Monty Hall opened door number 2 and same thing treatment can be done when Monty Hall opens door number 3 also. You will also see that. So this is 1 divided by 6. This thing, and over here I chose 1, door was in price 3 and Monty Hall opened 2. Okay, this is 1 by 3 multiplied by 1. Okay, I hope this is that. So this is 1 by 3. Okay, these are the two possibilities now. So these are the two possibilities for the Monty Hall when he opens the door 2, and these are my probabilities, computed probabilities. Now what should I do is, now I should see basically if he opens these doors, what is the probability? Now I'll have to just reshuffle these probabilities. So these things happen and I'll give these probabilities 0. I'll give them 0 probability. I'll have to only reshuffle this. So if I reshuffle this, so what is the case then? So I'll have 1 by 6, 1 by 6 and 1 by 3. So now this is my new sample space. So for this sample space, I have to renormalize the thing. So how to renormalize? I'll have to basically make them as 1. So I think if I multiply with 2, so this will be 2 by 3. Let's say if I do this, so 1 by 6 divided by 1 by 6 plus 1 by 3, something of this sort. So you have to compute this. So we basically are multiplying with, you're making denominator 2. So this can be written as 1 by 6. So this is 3, 6, 9 by 18. And this is 6, 1, 6, 3. So this is 1 by 1, 3 by 9, 1 by 3. So this is 1 by 3 over here. So this is 1 by 3 and this comes out to be 2 by 3. Okay, I just reshuffled it. You can reshuffle it. The calculation is pretty easy. So again, I'll reiterate it over here. So I said I chose the door 1 and these doors can have price. This is Monty's door. Now I am saying, okay, let's say Monty opens door 2 based on my initial choice. Okay, based on this, Monty opens door 2. So if he opens door 2, now I am making calculation based on that. The probability of this path is 1 by 6. Probability of this path is 1 by 3. Now if this thing happened, if Monty opens door 2, now I'll have to reshuffle probabilities. I'll have to make this 1 by 6 and 1 by 3 equal to 1. I'll have to basically reshuffle the probability. So this comes out to be this 1 by 6 converts to 1 by 3, and this is what 2 by 3. This is 1 by 3 and this is 2 by 3. Now what is the probability of switch? So when will we switch? So you have 1 and he open 2 and you will basically choose 3. So here when you choose 3, so here you will win. In this situation you will win. So here you will lose because you had first door, the first door also had price. You will lose. So in this path you will lose. So in this path you will lose, and in this path you will win. So what is the winning probability then? The winning probability is 2 by 3. How many of you understood this? So I'll summarize the setting again in a couple of minutes so that you, once you watch the recording, you will understand it better. The first thing is, here the problem is symmetric. I am saying I can make this diagram for all the 3 doors. Choose 1, choose 2, choose 3. Now this is symmetric, so I can just make the study on maybe this case. So choose, let's say we assume that we chose the door number 1. Now the car can be equally likely in any of the doors, 1, 2 or 3. So I am giving them equal probability in here. Okay, so that is here 1, 2 and 3. That's I'm giving 1 by 3 probability. After that, what I'm saying is, now you have door number 1. If the car is in door number 1, the Monty has 2 choices because he opens the empty door. So he can open door number 2 or he can open door number 3 with equal probability. And I also said that there are variants of problem where these probabilities can be different. The calculation will be different again that time. In the second scenario, when we chose 1 door and car is in door 2, the Monty is now forced to choose door number 3 because that's the only empty door he has. And similarly, in this case also, he is forced to choose door number 2. Now we have to compute the probability of winning if we switch, given that Monty opens the empty door. Okay, let's assume again the problem is symmetric. I could have said Monty opens door number 3 in this case or door number 2. Okay, we'll do a treatment on door number 2 first, and the same discussion will follow on door number 3 also. So if he chooses door number 3, if he chooses door number 2 to open, okay, and now in this case, in this path, the path that I'm making with blue, so this path is basically the losing path because you were choosing door number 1 and the car was also in door number 2. If you flip it to your choice, so you will switch to door number 3 here, but you will lose this price. So in this path you will lose the price. So along this path you will win the price. Why? Because you initially had chosen door number 1, but Monty opened door number 2. So here if you switch, so you will be at door number 3. That is the door which has the price. So if you choose this path, so what will happen? You will win the price. So the probability of this actually initially was this much and this much, 1 by 6 and 1 by 3. Now once you know that this happened, okay, now you will reshuffle the probability because these two will have probability 0 now. And even once you renounce the probability, you will get a probability of this is 1 by 3 and probability of this is 2 by 3. So this is basically giving you chance. If you switch, you are winning then with this probability. Same treatment can be done for this 3 also. So for this 3, what you can do is you can have this path or you can have this path. So in this particular case, when the door 3 was opened, so in here if you have 2, so you will switch from 1 to 2 because 3 was opened now. So here you will win. In this case you will win if the Monty Hall opens door number 3. So in this case you will lose. Okay, why? Monty Hall has opened 3, actually price was in 1 and you also opened 1. So what probability was there? Again the same case. Here the normalized probability will be 1 by 3 in this case and 2 by 3 in this case. So the chances are 2 by 3. So the intuition that we discussed was, initially you have higher chances of going wrong. So when you choose the door, so you have 1 by 3 chance of winning initially. Okay, so if you now at the final stage say I'll shuffle the door, I'll switch my choice. So basically you are saying that I was initially less confident I'll get it right. I was more confident I'll get it wrong. So if you are given chance to switch, you will say I'll switch at the end. Why? Because now I am turning that initial losing probability into winning one because I just am swapping my decision. Okay, this is one way of doing it. This is one way of doing this problem. So we can also do this by using total probability. Okay, so what the amazing thing about probability is that it grants you a wishful thinking. So if you sometimes wish something, it grants you and you can perform calculations on that. Okay, so amazing thing about probability is probability grants wishes. You can write it somewhere. Why? I'll show you how. How does it grant you wishes? So let's say if you wish something, so you could sometimes wish something. You'll say that, okay, I wish if I knew this information, maybe I could have solved this. Okay, so if you somehow wish, let's suppose car in which door the car is, so I could have solved this problem. So I'll introduce some notations and then I'll do this. So let's suppose S is the probability of success or winning. This is a probability of winning or success if I switch. This is a notation I'm introducing. Then let's suppose I'll introduce one more on the DJ. DJ is the jth door has the price. Jth door has the price. So what I said is, I said probability grants your wishes. So if you wish for something, so if you use conditional probability, it will seem that you assumed something and you made calculations and then your wish will be granted. So now the probability of success. So probability of success, what is this probability equal to? Okay, what I can do is I can say something of this. I can use law of total probability. I can say, let's say this is, I have to compute success. Okay, success can be by door 1, by door 2, or door 3. Okay, so I can write it like this. Probability of success is equal probability of door 1 intersection success, that is probability of door 2 and success plus probability of door 3 and success. Okay, now you know this. I can again write this. Probability that I'll get successful given that door 1 has the price. Okay, multiply the probability of door 1 plus probability I'll be successful given door 2 has the price, multiply by probability of door 2 plus probability of success given door 3 has the price, multiply by door 3. Okay, now let's assume door 1 actually has the price. Okay, this again a symmetric problem. So what you can do is, so probability of this, probability this has the price. So what will happen basically, I'm just choosing this value. So let's write it like this first. Given this door 1, so what's the probability of d1? So this is all 1 by 3, so I can just write 1 by 3, 1 by 3, 1 by 3 for everybody, 1 by 3 plus probability s given d2 multiply 1 by 3, probability s given d3 multiplied by 1 by 3. So is it going out of the screen? I suppose yes. So let's write it here. This is probability of s given d3 multiplied by 1 by 3. So what I used is, I basically use total probability over here. So I said, let's assume door j has the price. Okay, now what you can do is, if I assume that say door 2 has the price, say door 2, if I chose door 1, if I chose door 1 initially and I assume door 2 has the price. Okay, now this is the switching probability. So what we basically do is, should I switch? So if you see this, so this over here will get, because now door 2 has the price, so I chose the door 1, door 2 has the price, so it basically depends on what is Monty's choice. So this will become 0 because given that this dj door j has the car, so here d2 has the car, so this basically becomes 0. So this is 1 by 3 plus, so this over here will become if I switch, in this case probability of success, if I switch given that this has a price, so I have initially chosen door 1, so in this case if I switch I'll get 0 probability. So in this case here, now door 2 has the price, initially I have chosen door 1, so what will happen is I'll win this with 1 probability, multiply 1 by 3 plus, in this situation also, now door 2 has the price. Okay, I initially chose the door 1, so given if I switch, so what will be doing is 1 multiply 1 by 3, again I'll win this in this situation, because if I chose door number 3, let's suppose, and door number 2 has the price, if I switch I'll again switch the door number 1, so this over here becomes 2 upon 3 again. So this is by using the total probability. Okay, again reasoning it from the first principles is, you basically have this s, you break it down into 3 disjoint cases. So in that you first write these things, and then what you do is you come up with this formulation over here. Okay, then you assume one thing, so you assume that, let's suppose if I choose one of these doors, and you will see that switching probability will give you 2 by 3. Yes, I have a question, I think. Yes, question.
Once we know where the car is. So
wait, let me just pause the recording and I'll take the question. So now in this case also, if you see, we initially build the intuition, then we perform simulations, and based on the simulation we then once we had the tools of probability, once we had the tools of conditional probability in this particular case, so we could derive the same results mathematically also. So your intuition can be wrong sometimes, but if you derive it mathematically, then you should somehow realign your intuition. So that's what we did with these 2 problems. We did the problem first on medical paradox. Basically paradox are nothing. If the paradox actually existed, then the world would have not been the same. And paradox basically is when you think of something but it looks counterintuitive to your thinking. So that's what paradox is called. So here, if the first thing that we saw was medical paradox, and then we saw this Monty Hall problem, it again looked counterintuitive. The probability should have not been let's suppose 2 by 3, the probability that we actually got. But after building the intuition, once we do it mathematically also, the mathematics is giving the same answer. So what you do now is, let's suppose if you have some probability, so first think it intuitionally. If you think that intuition can be wrong, keep on doing the problem mathematically and see if you are mathematically coherent, and if you are making all the calculations right, and say that, oh, this is the probability. If you are convinced about that you have made no wrong calculations and all the things that you have done in this is right, then rethink your intuition and think if what you were thinking initially was wrong, and how can you realign the intuition with the mathematics. Because majority of the times, if you have done the probability calculations right, if you have used the right tools, you will be landing at the right answer. Then you will have to realign your intuition. But as I said, sometimes your intuition is also right. So it's not a probability is counterintuitive. It means that you should shut up your common sense. You should just shut it down, and you should whatever comes to your mind, you should say opposite of that. Not every time. So what you should do is believe in maths, but first you should be making sure that the calculations you are making, the tools you are making is right. Once you are sure that okay, I have used the right tools, I have performed the calculation, this is what the mathematics tells me, and after that if it feels counterintuitive, you will have to question your intuition, you will have to realign your intuition according to what probability is saying. Okay, so with this I'll conclude today's session. So in the next session we'll probably take more problems like Simpson's paradox, Gambler's rune, or other paradoxes, and then we'll move on to maybe random variables and stuff like that. So if you have any questions, I'll be willing to take them right now.